Chapter 7 Chemical Quantities. In chemistry, we calculate and measure the amounts of substances to use in the lab. Actually, measuring the amount of substances is something you do every day. When you cook, you measure out proper amounts of ingredients so that you don't have too much of one and too little of another. At the gas station, you pump a certain amount of fuel into your gas tank. If you paint the walls of your room, you measure the area and purchase the amount of paint that will cover the walls. If you take a pain reliever, you read the label to see how many tablets of aspirin or ibuprofen are needed. You read the nutrition label on food packaging to determine the quantities of carbohydrate, fat, sodium, iron, or zinc. Each substance that we use in the chemistry lab is measured so that it functions properly in an experiment. The chemical formula of a substance tells us the number and kind of atoms it has, which we then use to determine the mass of the substance to use in an experiment. Similarly, when we know the percentage and the mass of the elements in a substance, we can determine its formula. Section 7.1 The Mole. At the grocery store, you buy eggs by the dozen or soda by the case. In an office supply store, pencils are ordered by the gross and paper by the ream. Common terms such as dozen, case, gross, and ream are used to count the number of items present. For example, when you buy a dozen eggs, you know you get 12 eggs in the carton. Avogadro's number. In chemistry, particles such as atoms, molecules, and ions are counted by the mole, a unit called Avogadro's number that contains 6.022 times 10 to the 23rd items. Avogadro's number is a very big number because atoms are so small that it takes extremely large number of atoms to provide a sufficient amount to weigh and use in chemical reactions. Avogadro's number is named for Amedeo Avogadro, an Italian physicist. 6.022 times 10 to the 23rd is 6022 and 20 zeros after it. 1 mole of any element always contains Avogadro's numbers of atoms. For example, 1 mole of carbon contains 6.022 times 10 to the 23rd carbon atoms. 1 mole of aluminum contains 6.022 times 10 to the 23rd aluminum atoms. 1 mole of sulfur contains 6.022 times 10 to the 23rd sulfur atoms. 1 mole of an element equals 6.022 times 10 to the 23rd atoms of that element. Avogadro's number tells us that 1 mole of a compound contains 6.022 times 10 to the 23rd of a particular type of particles that make up that compound. 1 mole of a molecular compound contains Avogadro's numbers of molecules. For example, 1 mole of carbon dioxide contains 6.022 times 10 to the 23rd molecules of carbon dioxide. For an ionic compound, 1 mole contains Avogadro numbers of formula units, which are grouped in ions represented by its formula. For an ionic formula, sodium chloride, 1 mole contains 6.022 times 10 to the 23rd formula units of sodium chloride. Table 7.1 gives an example of number of particles in some 1 mole quantities. We can use Avogadro's number as a conversion factor to convert between the moles of a substance and the number of particles it contains. 6.022 times 10 to the 23rd particles per mole and 1 mole per 6.022 times 10 to the 23rd particles. For example, we use Avogadro's number to convert 4 moles of iron into atoms of iron. We want to get rid of moles of iron, so we put moles of iron on the bottom, and it's 4 moles of iron times 6.022 times 10 to the 23rd atoms of iron divided by moles. Moles cancel. Multiplying gives us 2.41 times 10 to the 24 atoms of iron. We can also use Avogadro's number to convert 3.01 times 10 to the 24 molecules of carbon dioxide to moles of carbon dioxide. 3.01 times 10 to the 23rd molecules, we want to cancel molecules, so we put it on the bottom and we put moles on the top. When we multiply, we get 5.00 moles of carbon dioxide molecules. In calculations that convert between moles and particles, the number of moles will be small compared to the number of atoms or molecules, which will be large. Moles of elements in a chemical formula. We have seen that the subscripts in the chemical formula indicate the number of atoms of each type of element in the compound. For example, 1 mole of ammonia consists of 1 nitrogen atom and 3 hydrogen atoms. If we have 6.022 times 10 to the 23rd molecules, or 1 mole of ammonia, it would contain 6.022 times 10 to the 23 atoms, or 1 mole of nitrogen, and 3 times 6.022 times 10 to the 23rd, or 3 moles of hydrogen. Thus, each subscript in the formula refers to the moles of each kind of atom in 1 mole of a compound. For example, the subscripts in the ammonia formula specify that 1 mole of ammonia molecules contains 1 mole of nitrogen atoms and 3 moles of hydrogen atoms. Atoms in a molecule: 1 atom nitrogen, 3 atoms of hydrogen. Moles of each element in 1 mole of a compound: 1 mole of nitrogen, 3 moles of hydrogen. Aspirin, C9H8O4, is a drug used to reduce pain and inflammation in the body. Using the subscripts in the chemical formula of aspirin shows that there are 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. The subscripts of the formula of aspirin, C9H8O4, also tell us that the number of moles of each element of 1 mole of aspirin: 9 moles of carbon, 8 moles of hydrogen, 4 moles of oxygen.